Hello friends, welcome to Engineering Funda family. In this video, I'll be going to explain you two designing problems based on Astable Multivibrator using Operational Amplifier. Before you see this video, I request you to go through my last video based on frequency derivation for Astable Multivibrator using Operational Amplifier, in which I have explained frequency calculation for asymmetrical astable op-amp, as well as I have explained frequency calculation for symmetrical astable op-amp. If you have seen this video, then you can easily design questions based on astable multivibrator using operational amplifier. Here I'll be solving two questions. So before I start with solution, I want you to try those questions first. So this is question number 1. Freeze the video in between. And this is question number 2. I hope you might have tried these questions. Now I'm going to solve question number 1. See, in question number 1, we are given with astable multivibrator that is producing output of 5 kHz and that is having 50% of duty cycle. If you have 50% of duty cycle, what it means? It means that you have T on is equals to T off. Here we have T on that is equals to T off. Means we have 50% of duty cycle. If you have 50% of duty cycle, then you will be designing symmetrical astable multivibrator. So this is what the basic circuit which we have for symmetrical astable multivibrator that I have already explained in my earlier videos. Here I'll explain you how to identify value of components like R1, R2, RF and C. To have values of these components, first of all, you should know what is the basic equation. I have explained that equation even. See, equation is frequency is equals to 1 by T, where value of T that is 2 RFC ln of 2R1 plus R2 divided by R2. So this equation that I'll be using over here for identification of value of components. Let me explain you how. See, here we have been given with frequency that is of 5 kHz. So here we have value of frequency that is of 5 kHz and that is 1 divided by time period T. So based on that, one can have value of T that is 1 divided by 5 kHz. So 1 by 5 into 10 to the power 3, that will be resulting into 0.2 millisecond. And see, value of T that I have explained in derivation. What is that basic equation? Value of T that is 2RF into C ln of 2R1 plus R2 divided by R2. Now here we need to select value of components. So first of all, let me explain you how to select value of components. See, what we will be doing is we will be assuming few values over here. Like you can assume value of R1 and R2 initially. Let us assume R1 that is equals to R2 that is of 1 kilo ohm. Right. So if you assume that this ln part that will be there with you, this T that we have already calculated based on frequency. So out of RF and C, you can assume value of one component. Let us assume value of C that is equals to 10 nanofarad. So if you assume these values, you can identify value of RF. And once you identify value of RF, we will be having value of all the components that will be producing frequency of 5 kHz, and we will be using this equation. That is the equation of symmetrical astable multivibrator. So that will be producing 5 kHz of frequency which is having 50% of duty cycle. So let us calculate this. So here we have value of T that is of 0.2 millisecond, right? That is equals to 2 into RF into C that we have assumed, that is 10 into 10 to the power minus 9, nano means 10 to the power minus 9, ln of 2 R1 plus R2 divided by R2, R1 and R2 that is of 1 kilo ohm. If you substitute 1 kilo ohm over here, then 3 kilo ohm divided by 1 kilo ohm, that is resulting into 3 over here. So here you just need to solve this in calculator, that is 0.2 into 10 to the power minus 3 divided by this 2 and this 10 to the power minus 9 into 10 into ln of 3. You just solve this in calculator, you will be getting value of RF. So let me check what is my answer for RF. See, RF should be 9.1 kilo ohm over here. So that is how one can identify value of all the components. See, RF that is 9.1, C that is of 10 nanofarad, R1 and R2 that is of 1 kilo ohm. So let us substitute the values in circuit. So R1 that is of 1 kilo ohm, R2 that is of 1 kilo ohm, C that is of 10 nano, right? And this RF that we have calculated that is of 9.1 kilo ohm, right? So this circuit that will be producing square wave of 5 kilohertz with 50% of duty cycle. Now let us have waveforms. So here waveforms are having frequency of 5 kilohertz, right? So here T on and T off both are having equal time duration. Total time duration is T. Total time duration is T, that is of 0.2 millisecond. So T on and T off both will be of 0.1 millisecond, right? And here V2 that is a voltage across this capacitor. So voltage across capacitor that is varying in between minus V1 to plus V1. And what is the value of V1? Value of V1 that is here this V out into R1 divided by R1 plus R2. That is what I have explained you in theory. And during T on, this V2 that will be changing from minus V1 to plus V1, and during T off it will be changing from plus V1 to minus V1, and that is how waveforms will be appearing, right? So that is what I have explained in theory portion, right? Right now you just need to understand how values of components are there, right? Let us solve second question now. See, in second question what is given. In second question we need to design a stable multivibrator that is producing output of 10 kilohertz and that is having duty cycle of 40%. Here duty cycle is not equal to 50%. What it means? It means T on and T off both are not equal. If it is not equal, then we need to have asymmetrical astable multivibrator. So this is what the basic circuit which we have for asymmetrical astable multivibrator, that also I have explained in my earlier videos, right? Here what I'll do is I'll be explaining you component selections, like what should be C, what should be RF1, RF2, R1 and R2, right? So first of all you need to understand this frequency with 40% of duty cycle. So here we have been given with frequency F that is of 10 kilohertz. Based on that one can have time period T, that is 1 divided by F. So that is 1 divided by 10 kilo. So we'll be having 0.1 millisecond. Now once we have value of T, we need to identify what should be T on and what should be T off. So here we have been given with duty cycle 0.4, right? And what is duty cycle? Duty cycle is T on divided by total time period T. So based on that you can have value of T on. What is T on? T on will be 0.4 into T. T is 0.1 millisecond. So 0.4 into 0.1 milli, that is 0.04 millisecond. So now we have value of T on, right? Based on that one can have value of T off. You see how. What is T off? T off that is total time period T minus T on, right? See, T on plus T off, T on plus T off that is equals to T. So here T off will be T minus T on. So 0.1 minus 0.04 that is resulting into 0.06 millisecond. So now we have values of T on and T off, and based on this we can have component selections, right? We can have component selections. So here see components are C, R1, R2, RF1 and RF2. So here, first of all, I'll explain you how equations were there. You see, I have explained those equations in my last video. See, T on is Rf1C ln of 2R1 plus R2 divided by R2, and T of is Rf2 into C ln of 2R1 plus R2 divided by R2. Right. So here, let me write equation first for T on. So if you write equation for T on, see, T on is how much? T on is Rf1 into C into ln of 2R1 plus R2 divided by R2. So here, see, first of all, you need to assume few values. We have T on, right? You need to assume values of C, R1 and R2, right? So if you assume value of C, R1 and R2, let us assume R1 is equals to R2 and that is equals to 1 kilo ohm, right? And let us assume value of C that is equals to 10 nanofarad. So based on this, one can calculate value of Rf1. The reason is T on that we have, right? So let us substitute the values. So here T on that is 0.04 millisecond, right? That we have calculated. That is equals to Rf1 that we need to find. Value of C that we have assumed that is 10 nano. So 10 into 10 to the power minus 9 into ln of, see, R1 and R2 both are equal. So 2 plus 1 that is equals to 3. So ln of 3 that we need to have. Now we need to simplify this to get the value of Rf1. So here Rf1 will be how much? That is 0.04 into 10 to the power minus 3 divided by 10 into 10 to the power minus 9 into ln of 3. You just solve this in calculator, you will be getting value of Rf1. Let me check what is my answer. So Rf1 that will be 3.64 kilo ohm for this particular case, right? Similarly, we need to use T of equation. So T of equation is what? T of equation that is same as T on equation. In T of equation, we will be having Rf2 into C ln of 2R1 plus R2 divided by R2. See, during T of time period, Rf2 is getting activated because of D2 is on. And during T on time period, Rf1 is getting activated due to D1 is on, right? So that is how equations are there. Now we need to substitute all the values. So what is T of? T of is 0.06 milli means 10 to the power minus 3 that we have calculated UC. And Rf2 that we need to find, and value of C that we have assumed that is 10 nano into ln of R1 and R2 that is of 1 kilo. So ln of 3. Now just solve this. So Rf2, if you solve this, you will be getting value of Rf2. Let me check what is my answer. So Rf2 that has to be 5.46 kilo ohm. So now we got the value of Rf2. We got the value of Rf1, right? And we have assumed values of R1, R2 and C. So that is what we can place in the circuit over here, right? Which will be producing frequency of 10 kilohertz and 40% of duty cycle. So R1 that we have selected that is 1 kilo ohm. R2 is of 1 kilo ohm. C that is of 10 nano. Rf1 that we have calculated, Rf1 is 3.64 kilo ohm. Rf1 is 3.64 kilo ohm, and Rf2 that we have calculated that is of 5.46 kilo ohm. 5.46 kilo ohm. And if you have these components, then with this circuit we will be having asymmetrical astable multivibrator, right? That is having duty cycle of 40% and frequency of 10 kilohertz. Let us have waveforms. So here if you observe the waveform, we have T on over here, that is T on, and we have T off over here, right? T on time period that I have explained earlier, T on is 0.04 millisecond, right? And T off that is 0.06 millisecond, that even I have explained, right? During t on time period, waveforms will be increasing from minus V1 to plus V1, and during t off, waveform will be going from plus V1 to minus V1. That is how waveforms will be changing, right? Here one should know, see, during t on time period, time constant is there as per RF1 into C, and during t off time period, time constant is there as per RF2 into C. And value of components that I have explained you how to identify. So if you understand this equation in this way, you can design astable multivibrator for symmetrical as well as for asymmetrical case. You should know, if you have symmetrical astable multivibrator, in that case, T on and T off both are equal, right? But if you have other than 0.5 duty cycle, then you will have to design astable multivibrator for asymmetrical case, where RF1 and RF2 along with diode that you will have to connect. Here with symmetrical case, instead of this circuit combination, you will have to use RF resistance only. I hope now you got the point how to design circuit, and by using these equations you can solve any question, right? But first you need to understand how fundamentals are there. All the fundamentals that I have covered in my earlier videos of this lecture series. Still, if anything I would like to share, please note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.